Hello. It's only two of you so far, Jason and Justin.
Hello.
It's 11
Hi there.
a.m. There's one more. I'll give it another minute and see how many people show up. So how is everyone holding up? Say something. You can unmute.
It's pretty busy with all the projects due at once.
No. Oh, for some reason I can't hear you guys. Oh, hold on 1 second. Ah, okay. Now say something. Hello?
It's pretty busy with end of the semester and all the projects being due at the same time.
Ah. So you think you guys want to have next Tuesday's lecture off, or do you want me to do something next on Tuesday? Just let me know. I have some plans for what to cover on Tuesday, but if not enough people show up, I probably won't bother. Okay, let's see. I lost my screen sharing for some reason. Oh. Can you guys, you don't see my iPad, right? You don't see the notes.
No, we can see.
No.
Go back to Zoom. Okay. Now should be shown. Ah, good. Well, looks like there are 6 of you now. Should we wait for another minute? Do you guys have any questions about what we did last time or anything else about your projects? If you making good progress on that so far? People are quiet, I guess. All right. Let's see. We'll start at 11:05. Giving people time to join.
So do you have any plan for the next Tuesday class?
Well, I didn't really get any suggestions from you guys, but I was thinking, it's among the topics I was thinking about covering. It'd be difficult for me to actually go into any details on any problem in one lecture. But what I could do is just at least introduce the different problem formulations and then give you pointers on where to look for more details if you're interested. And some of the things we could discuss are things like semi-definite programming, which I didn't really talk about, but it's mostly it can be used as a computational technique. So you can write a lot of convex programs as semi-definite programs. Once you write it that way, there are very efficient ways to solve the program. So solve the optimization problem. So that's one topic we can discuss. A lot of modern convex optimization problems can be posed that way. Another topic is stochastic gradient descent, which I kind of briefly mentioned when we talked about neural networks earlier. But what that means, and the analysis, of course, requires knowledge of random processes at the level of 534, which I know most of you haven't had. So, but I could still at least introduce the problem, and even if even if we don't actually discuss what the convergence results are and so on. So that's one thing. And another topic is what's called an extension of the idea of method of multipliers. It's called ADMM, which is also commonly used in many applications. So maybe a fourth topic might be something like coordinate descent. So I can take this, just introduce you to these 3 or 4 problems, and then point you to places where you can read more about them if you're interested. So, but it looks like there are only like 7 people who came to today's class. So, so if it's this level of engagement, I'm not going to bother. So, but we'll see. Maybe more people will join. All right. So, support vector machines. Okay. So let's talk about that. I said that it's a really good example to illustrate the power of duality, okay, and constraint optimization. So what's the problem, right? So this is the machine learning problem of classification. Okay, so you're given a feature vector, okay, which could be say an image, right? So image represented as a vector in n dimensions, and you want to assign a label to the image. For example, there could be images of cats and dogs, and so the cat images are, say, labeled +1 or something like that, and dog images are labeled -1. And so the idea is that if you're given a bunch of training data, and these are labeled inputs. In other words, these are pictures for which you know whether it's a cat or a dog, for example, right? And so you know the YIs for these training data. And we talked about this also in the context of neural networks before. And you want to build a classifier to predict a label. So the difference between classification and other kinds of problems, machine learning problems, is in classification, the label or output takes only values in a finite set, 1 through m, or A1 through AM, okay, more generally. And you'd like to predict this label for a new input, okay? And we'll focus today on the problem of binary classification, although these ideas can be generalized to more than 2 classes. So in binary classification, we have that the output or the label belongs to +1 or -1. And the example, as I said, is you might be representing an image, and images of cats might correspond to +1, or dog might correspond to -1. Okay. All right. So we're going to build a classifier, and specifically we're going to talk about a linear classifier. So a linear classifier looks at these points x in n-dimensional space and draws a linear boundary to distinguish between the 2 classes, right? +1 and -1. So what's a linear boundary is basically of this form, and we have seen this form several times in this class. So it's of the form W transpose X plus B equal to 0, right? And this is a hyperplane in n dimensions, right? Hyperplane, which is a line for in 2 dimensions. So with just x1 and x2, it's a line. but more generally, it's like this is going to be a hyperplane. Okay, like in 3 dimensions, a hyperplane is like a sheet of paper, right? I don't have a sheet of paper here. Convenient. Okay, here. Find a sheet of paper somewhere. Oh, that is not really a sheet of paper, but yeah. So in 3 dimensions, that would be a hyperplane, right? Right. So above the hyperplane, we'll say that we have W transpose X plus B is bigger than 0. And one side of the hyperplane will be bigger than 0, and the other side of the hyperplane will be less than 0. On the hyperplane itself, W transpose X plus B equal to 0. Okay. So, and we'll say that when you have you have plus ones above the hyperplane and minus one below the hyperplane. So whenever a new point X falls above the hyperplane, we'll classify it as a plus one, and falls below the hyperplane, we'll classify it as a minus one. So that's a linear classifier. Right? Any questions so far? All right. So the question is how to design, how to construct this linear boundary from training data. Okay, so let's look at the following case. This is called a linearly separable case, where say the data points corresponding to plus one are these blue points, and the ones corresponding to a minus one are these red points. So I distinguish them between colors. These could correspond to pictures of cats, and these correspond to pictures of dogs, right? And they are points in n-dimensional space. Okay, we can only draw 2 dimensions on a piece of paper, so that's why we just have 2 dimensions here. But this example is one for which the training data is well separated, in the sense that they're so-called linearly separated, in the sense that I can draw a hyperplane or a line in 2D that separates the data. Maybe I should use a different color for the line. So I can draw a hyperplane like this to separate the red and the green training data points. Okay, so this could be the one that I just drew is a candidate for my classifier. So I found a way to distinguish the pictures of cats and dogs with this hyperplane. And so now if I get a new picture, if it lies above this line, I'll call it a cat, and below this line, I'll call it a dog. Okay. But is this the best line I could have drawn? Right. In fact, there are infinitely many hyperplanes separating these 2 classes. Once these classes are linearly separable, they can be separated by an infinite number of planes. Okay, I could have drawn a line like this, for example. Okay, that separates, okay, barely separates, it almost touches the red point there, right? And then I could have drawn a line like this. So among all these lines, okay, which one should I choose, right? So this line actually separates the blue and the green points, but basically you can see that this blue point is awfully close, and this is almost touching the line, and this red point is almost touching the line. So it's not doing a very good job of separating the training data. It's separating it, but it's not doing a great job. This line, the one that I drew first, is a little better, right? Because there's a larger gap between the closest blue point to the line and the closest red point to the line. Okay. So anyone have any ideas, or how should I choose this boundary so that I get good separation between the classes? Okay. So that's the idea. You want to do this, and here's an example. Actually, this is the solution to this, what's called a support vector machine for the linearly separable case. This is this is the line. This is the hyperplane, right? The one in solid. The one in solid. It's drawn in such a way that it maximizes the smallest the distance of the point from the line, from the hyperplane. Okay, so this is the one that among all these points, if I look at the distance of all these points to this boundary on this side, and from all these points to the boundary on this side, this line actually results in the maximum so-called margin. So this maximizes the margin between the training data points. Okay. So that's the idea. So pictorially, I guess you can see that this is a good solution, right? The one that results in the maximum margin, the maximum gap between the classes. Okay. Something like this, a line like this, wouldn't be as good, right? Everyone see that? Any questions on what the goal is in the support vector machine problem? You're not saying anything. You can unmute and speak, or and these lectures are, as I said, that these 3 lectures after the second midterm were all meant for giving you some information. I'm not going to be testing you on it. So if you have any questions, do ask. Treat it more like a seminar or something. Okay. All right. So how do we pose this as an optimization problem? So in order to do that, this optimization is based on the notion of distances, right? We want to maximize this gap, this distance. So first, let's understand how do we measure the distance between a point and a hyperplane? Right? So in particular, let's look at the ith point, xi. This is the ith training data point. Okay, and say let's assume that the label for that training data point is +1. So W transpose xi plus b is positive. Okay. Let's write that red. So it's sitting on this side of the hyperplane, and I want to know what the distance between this point xi and this is. Okay. So that's cool. I want to know the distance of xi to the hyperplane. Okay, before we get to that, if I have a hyperplane like this, W transpose X plus B equal to 0, then I claim that if I look at this vector W, and I'm drawing it from the origin to the point W here, that if I look, it's going up in this direction, right? This is the direction of the vector. It has to be perpendicular to this hyperplane. So if I draw any line in the hyperplane that's sitting inside the hyperplane, any vector sitting inside the hyperplane, then W must be perpendicular. Why? Anyone?
Because that's the long.
That's what?
It's the longest distance.
Oh no. It has nothing to do with the longest distance. I'm saying, why is that this vector is perpendicular to this? So if I take the dot product of this vector and anything that's sitting on this line, it has to be 0. Why is that?
Oh, because it's orthogonal. Or
Aha. So let's see why that's true. Okay. So suppose I have x1 and x2 sitting in the hyperplane, are points on the hyperplane, right? So x1 and x2 So maybe this is a, I should call x1 and say this is x2. Then the line joining x1 and x2 is the difference between x1 and x2, right? Or x2 and x1, right? So so x1 minus x2 is in the direction of the hyperplane. But since x1 and x2 are in the hyperplane, we must have that W transpose x1, W transpose x1 plus B is equal to 0, and W transpose x2 plus B equal to 0. And so if you look at W transpose x1 minus x2, what is that equal to? That's equal to B minus B, which is equal to 0. So any vector that's sitting along the direction of the hyperplane is going to be orthogonal to W. Right? So W is orthogonal to the hyperplane. Can you see that? Okay. So now let's look at W, take W and divide it by its magnitude, and that'll give me a unit vector in this direction. So W divided by the magnitude of W is a unit vector in this direction, and it's a unit vector that's perpendicular to the hyperplane. So if I take xi and subtract out psi as the distance of xi to the hyperplane, and I'm going in the direction of this W vector. So I'll hit exactly a point on the hyperplane, right? So if I take a unit vector in the direction perpendicular to the hyperplane, and I start with xi and come down by the amount psi, then I'll hit a point on the hyperplane. So xi minus psi W divided by W is a point on the hyperplane. But any point on the hyperplane must satisfy the condition that W transpose that point plus B is equal to 0. So, and we can simplify that to be W transpose xi minus psi I. Now W transpose W divided by the norm of W will give me another norm of W on top. One at the bottom cancels out. And then I'll get a plus B equals 0, from which I conclude that psi I must equal W transpose X plus B divided by W. Right? Everyone see that? Now, psi I is the distance, so it's positive. And in this particular case, W transpose Xi plus B is positive. But if I was on the other side from here and then measured my psi this way, then W transpose Xi plus B would be negative. So psi I in that case would be if you do the same calculation, you'll get that psi I would be the absolute value of this. More generally, this would be the absolute value of W transpose Xi plus B divided by. So this covers both points that are below and above the hyperplane. Okay, so I figured out now how to measure distance between a point and a hyperplane. Okay, and we could actually have solved this problem in a slightly different way using what you learned in this earlier in this class. So we could actually think of this as a convex optimization problem. You want the distance or the distance squared is the minimum of xi, of the difference between xi and z squared, such that z is on the hyperplane, right? So this is a constraint optimization problem. In fact, this is a convex constraint. It's a convex function, it's a quadratic function actually. So you can solve this by taking the Lagrangian, setting the gradient of the Lagrangian to 0, and then if you solve for the Lagrange multiplier and the corresponding z star, you end up with exactly the same thing for psi. Okay, so you can go home and make sure that that's correct. Okay, but I just wanted to give you a geometric proof first for how to compute this distance. Any questions about how you compute the distance between a point and the hyperplane? Okay. So let's actually think about this a little more generally in terms of the label. So this result. So yi is +1 is the same as the point being on the top of the, to the right of the hyperplane, or above the hyperplane. I'll think of it that way. And yi is -1 is when the point is below the hyperplane. And so this distance of the point to the hyperplane psi can be, which is the absolute value of this divided by the magnitude of w, can be also thought of as the product of yi and w transpose xi plus b. You want to see that? Because basically, whenever this guy is positive, yi is positive, so the product will be the absolute value in that case. And if this is negative, this is also negative, and the product will be the absolute value. Okay, so I can write this absolute value in terms of the product of yi and w transpose xi plus b. Okay, so now let's get back to our picture here. So our goal was to make sure that, and the SVM goal is to make sure that the distance of all these points to the hyperplane that I drew was as large as possible. By that I mean is, what I mean is that I want the smallest distance to be large as possible. Smallest gap, the worst gap, to be as large as possible. Okay. So we want to maximize over the choice of the hyperplane, and the hyperplane is characterized by the weight vector w and this the offset b. We want to maximize the minimum over I psi I. So this is actually a max-min optimization problem, and we don't really want to solve it that way. Turns out that you can. This is a trick that you can often use in many optimization problems. That you can replace the this objective by essentially either a lower or upper bounding. So if you're minimizing, you upper bound the objective. If you're maximizing, you lower bound the objective. And you look to maximize this objective under the constraint that the distance of the points is bigger than that number. So let me write it down, and then it will make sense to you. So I can think of this optimization problem equivalently as follows. I want to maximize, I'll introduce a new variable psi, right? In addition to w and b. So this is called an auxiliary variable. I want to maximize psi such that subject to yi, my distance of each, but this is the distance of each point in terms of w, bigger than psi for all I. Okay. If I do that, since I'm making sure that the distances are all bigger than this psi, this common psi, and I'm maximizing psi, then I'm guaranteeing that I'm maximizing the minimum of the psi i's. Okay. And this is this kind of posing changing the optimization. This problem is sometimes called epigraph optimization, and there's a discussion more generally about this kind of this trick in the book by Boyd, Boyd and Vanderbergy. There's one of the references for your course. Okay, and we may come across this trick again on Tuesday when we talk about semi-definite programming. Okay, so this is the optimization problem that we want to solve. Actually, I've started with this instead of starting with this max-min problem and converting to this. I could have just started with this. This makes sense on its own, right? I want to do this to find the the best boundary or best hyperplane. Okay, so now I'm going to do a slight change of variables. So I'm going to take a quantity and define a quantity called beta, which is this psi, this variable psi, times the magnitude of w. If I do that, I can rewrite the optimization problem. I can write chi as beta divided by w. So let me do that. Beta divided by normal w. And maximize over, instead of psi, I'll maximize over beta now. And then I'll write this thing in terms of beta. So yi w transpose xi plus b bigger than or equal to psi times w, which is beta. Okay. Now I'll do another change of variable. This is interesting. I'm going to take my w and divide it by beta, and b also divided by beta. So I'm going to scale my w by beta. So by doing that, basically I'm making this constraint, instead of being constrained by beta, I'll be constrained by 1. So in a way, what I'm going to do is I'm normalizing my variables, my hyperplane, such that I'm always shooting for a margin of 1, right? You can think of, I start off with margin being psi, the distance of the nearest point, psi, and I'll convert that to a margin of 1, okay, by scaling things. And again, scaling things doesn't really affect the hyperplane. Why? Because how's the hyperplane defined? It's defined by w transpose x plus b equals 0. I can scale this by any factor I want, and it'll still be the same hyperplane, right? But what will change is the distances of points to the hyperplane, because by scaling w, I'm also scaling this thing here. So I can actually affect the margin by doing that scaling. So, okay, so that's, again, let's get to what happens here. So this by doing this scaling, I'm maximizing 1 over w tilde now, right? So beta divided by w will become 1 over w tilde, and I'll be maximizing this over w tilde, b tilde, and beta, okay? Such that yi times w tilde transpose xi plus b tilde is bigger than or equal to 1 for all I. But here's something interesting that happened when I made this change of variables. Anyone notice something here in this optimization problem?
Beta is not related.
Ah, very good. There's no beta. Right? So basically you can forget about beta because it doesn't really appear in the problem anymore after doing the scaling. Okay. So, and I can actually drop the tildes now. Okay, because now I've taken care of things in the constraint. So I can drop the tildes and replace the variables as max 1 over W such that W transpose Xi plus B bigger than 1 for all I. Okay, so this is my final version of the SVM optimization problem. Okay, but I can also do the following. Instead of maximizing 1 over W, I can replace this by minimizing W. So it's the same thing. Okay, now this is starting to look more familiar. And in particular, if I want to maximize the norm, if I want to make it into a nice convex optimization problem, I can instead replace the norm by this quadratic. It's the same thing. So minimizing that was the same as minimizing the norm, subject to those constraints. So you do this, you get a quadratic program, which is nice. Okay, very nicely behaved optimization problem. So that's the SVM optimization problem. You want to minimize this quadratic function subject to these linear convex constraints. Okay. Now, why is it called a support vector machine? Why is it called? Where does that term come from? It turns out that this optimization problem is basically controlled largely by the xi yi's, and we'll see this actually in the dual. The xi yi's that satisfy the constraint with equality. Okay, and these xi yi's which satisfy the constraint with equality are the xi yi's that sit on the margin boundary. So let's look at the picture. These points here, this blue point here, and these two red points here. Okay, and there's usually going to be very few of these points. Okay, that actually sit exactly on the boundary, and these are the ones that satisfy the constraint with equality. These are the ones for which they sit exactly at the edge of the margin boundary. The ones, the minimum from this side and the minimum from this minimum distance from this side. Okay, and these are called the support vectors because they kind of support your your margin boundary in defining the hyperplane that separates the classes. Okay, so that's where the terminology support vector machine comes from. Any questions so far? So, no questions? All right, let's take a short break. And then when we come back, we'll look at a dual formulation of this SVM. And it will turn out that the dual is very useful in this context for a very, very special reason. And we'll get to that after the break. Okay. All right, any questions before we proceed? Anything you thought about in the last 2 minutes? Okay, so one thing you can see that this is a nice convex optimization problem with linear constraints, so you can easily check that Slater's conditions for strong duality hold. Okay, so rather than solving this problem, we can look at trying to solve the dual. And let's see what the dual looks like. Well, I mean, although if you really think about it, and this is not that hard of a problem to solve. You wrote programs in I guess your second programming assignment where you solved a problem exactly like this, right? Using the barrier method. So you can solve this problem relatively easily. But there's a real advantage of the dual, and that really comes out in what's called when you use something called a kernel. So we'll get to that towards the end of this lecture. So, but let's still look at the dual. So to compute the dual, we'll have to look at the Lagrangian. Which is, so the capital N data points, training data points. It's 1 minus yi times W transpose xi minus plus b. So, okay. So there's one little, okay, so we let the gradient with respect to W and B. If you take the gradient with respect to W first, and then set it equal to 0, you can easily see that that will give me that W. So this will just be W, it'll give me the gradient of this is W, and then the gradient of this part, it's linear, so it'll just give me xi, yi, mu I. So W, so from that I'll conclude that W equals, or W star if you want to call it that. Okay, and similarly, if I take the gradient with respect to B and set it equal to 0, then what happens is, so this part, this just is multiplying yi and mu I, and I'll just get the summation mu I yi equal to 0. Actually, I don't get an equation for B from this, but summation mu I. We'll talk about how we find B a little bit later. Okay, so if you plug this in, well, one thing we have to be a little careful about. So this gradient condition is all right, except that if mu I yi, this summation mu I of yi were not equal to 0, then by choosing B to be as large as I want, okay, I can make this thing go to minus infinity. So I have to be careful. This is similar to what happens here in when we looked at the dual of the linear program. So this thing here, this minimum of this quantity, can be made minus infinity as long as this quantity is non-zero, right? So we actually have to have as a constraint a summation mu I yi equal to 0. So in fact, it's not just that this is an equation that we use to solve for the optimum value of W and B to plug in to L, but it will also have to be used as a constraint when I look at the dual problem. Okay, and we'll get to that in just a minute. But if you plug in these equations back into here for L, you get the following. So I've written W is this summation W squared will be this times its transpose, right? And so I can write that as the double summation. And I'm writing it as double summation on purpose so that I see this dot product between xi and xj appearing here. This will play a role a little bit later. Okay, and similarly, if I plug in mu I yi equal to 0 here, then I'm going to be left with so that the b part that will go away, and I get mu I yi times then this w again. If I plug in this second summation. So there's a bit of a right over here. There should be another summation here. So this will give me another summation I equal to 1 to n, or j equal to 1 to n. So I'll this kind of form should be familiar from all the problems, even in your exam, when you wrote a dual function with a quadratic. Okay, you do get, when you plug things back, you get terms canceling, right? So you get so that's exactly what's happening here too. So if you notice that this w squared term, half w squared term, is actually the same as this term here. So the difference will give me minus half times just one of these guys. So this whole thing just becomes summation mu I equal to 1 to n minus half okay. So that's the dual function. And the dual optimization problem is to maximize this function such that we're subject to mu has to be non-negative for all I. And as I said, we need the constraint mu I yi equal to 0. And this comes from the fact that if mu I yi were not 0, I could make my Lagrangian go to minus infinity. Right? So this solution for the optimum for the Lagrangian makes sense only when mu I yi is equal to 0. Right? So that's why we need to add this constraint, additional constraint here. So this is a quadratic optimization problem also, just like the primal. Right? Quadratic optimization problem with linear constraints. Okay, and so if we solve the dual, okay, which is it seems to be a similar complexity solving the dual versus solving the original problem. But if we solve the dual, then we can get W star, the optimum value of W, as the summation from I equal to 1 to n. You just use this equation basically. You use this equation. So I'll plug in my mu star or I star. Okay. So one interesting advantage of the dual formulation is that very few of these mu i's are going to be non-zero, and the mu i's being non-zero will correspond to the support vectors, and the support vectors are going to be very, very few. Okay, the ones that the number of non-zero mu i's will be the number of support vectors. In this example, there were 3. Right. So that's one advantage. So once you compute the mu's, the optimum mu's, you can very easily compute the W star by just taking the linear combination with the mu's of the yi xi's. Okay, and there'll be very few terms in the sum. How about B star? So we didn't get an equation from B out of the gradient. So how should we find B star? Any ideas? Keep getting this notification. Any ideas how to find B star? What are the conditions do these Lagrange multipliers need to satisfy? What conditions do Lagrange multipliers need to satisfy when you have inequality constraints? Anyone remember? Or you've forgotten already because you're done with the exam? What's an important condition for Lagrange multipliers to satisfy? KKT. Which KKT conditions important for inequality constraints? Anyone? Oh boy, you go here. Either you're too shy or you've forgotten. Or I hope it's just that you're too shy. So complementary slackness, right? So we know that mu I star star then. So let's satisfy this condition. The constraint times mu I is equal to 0. So whenever the mu I star is positive, it must have 1 minus yi w star plus b. Let's call it b star maybe. For the 0. So b star must equal so you could choose any one of the support vectors, right? And so those correspond to the non-zero mu i's. And so take any one of those support vectors for which the constraint is satisfied with equality, and you can find the b star from that. And all of them should result in the same b star. It doesn't matter which one you use. Okay? So that's how you would solve it using the dual. Okay. Now let's address one other important point. What happens if the data are not linearly separable? So this is an example of that. Okay. So here I have a blue point that's here and a red point that's here, right? So there's no way for me to separate the blue points and the red points by a hyperplane. They're not linearly separable. I could use some complicated surface to separate them, but not a linear hyperplane, right? So I could have used a surface like this, something like this, okay, to separate the two, okay? But a line cannot separate these points. Okay, so what do you do in that case? In that case, what you do is you define the margin in the same way. You have a margin, okay, and you want most of the points to lie on either side of the margin, right? The red points on this side, the blue points on this side. But there's going to be some violation of the margin. Okay, so you allow for some violation. So in this particular case, this red point is on the wrong side of the margin. And so there's a violation which I'll call gamma I. This is the distance of the red point to the wrong side, from the wrong side. And similarly, here there's a blue point that's also on this side. It's not that much of a violation, but still a little bit of a violation. And this blue point is also violating. Okay, so there'll be a few points like this that violate the margin. All these other points are not violating, for which I'll give the penalty. The penalty gamma I is the violation, is for violation of the margin. And these points have zero violation, and these other guys have a violation of gamma I. Okay, so then I include that in my optimization. So I'm going to allow for some margin violation, but I'll control that margin violation. And things that are on the correct side of the margin have a penalty of 0. Okay, so rather than minimizing just half of W squared, I'll minimize this plus the sum total margin violation, and this is a control parameter that allows me to control how much I want to violate versus having a large margin. Okay, so just maximizing this subject to the constraints allows me to get a nice margin. But if I make my margin very large, then I'll get more violations. For example, in this picture, if I made my margin here this much, right, then all these points will start violating the margin. Okay, so it's a trade-off, and that trade-off is captured to this control parameter C. Okay, so C controls the margin violation. Okay, and again, we cannot satisfy anymore that yi times this is bigger than 1. That was for the case where you had a nice linearly separable situation. But here, all you can hope for is that it's bigger than 1 minus this violation. Okay, so the constraints changed. And this is only going to be an issue for points for which gamma I is non-zero. So these few points that are sitting in the margin. Okay, so we'll change the constraint for those points to be that 1 minus gamma I instead of 1, and we'll make sure that gamma I is bigger than or equal to 0 for all I. So this is a problem. Now we have these gamma I variables that we're optimizing over as well. Okay, so now we have instead of just having capital N constraints for each of the n data points, we have 2 times capital N constraints in the primal problem. And the amazing thing about this is called soft margin optimization. Okay, this is also called when the things are not linearly separable. This is called soft margin optimization problem. This soft margin optimization problem, the dual has almost the same form. Okay, and you can work this out at home. It's not that hard to see. And in fact, rather than having, so since you have 2 times n constraints in the original primal problem, you would have to have Lagrange parameters corresponding to each of these. So it would be 2 times n Lagrange parameters, right? One would think. Right? But it turns out that you can rewrite this optimization problem just in terms of just the mu's, just in terms of n parameters in the dual. Okay, and you can try. It'll be an interesting exercise. It's not that hard. You can show it at home, and ensure that this function d mu is exactly the same as before. It's the same d mu, this thing here, that we had in the hard margin optimization problem, the linearly separable case. Okay, and then we still have the constraint mu I y equal to 0, just like we had here. But instead of just having the mu's bigger than 0, introducing this C here, how this is captured. So this, you can think of these mu I less than C as capturing the constraints that gamma I are positive in the dual. Okay, so you don't need to introduce new Lagrange parameters, the same parameter, but it has a lower constraint and an upper constraint. So it's like a box constraint. Okay. So that's a nice thing. So in the dual, it doesn't really change that much. All right. Any questions? Okay. So now we'll get to why we want to actually solve this in the dual domain more precisely. And this comes from what's called the kernel trick. So what's the kernel trick? The kernel trick, what you do is you take the original features in the original space, right, as an n-dimensional space, where your feature vectors x is sitting. And rather than doing your separation of the data points in that original space, so trying to draw a boundary in that original space, you transform these points through a nonlinear transformation phi to a new space. And phi of x is typically, so phi is a vector transformation. So I might go from n-dimensional space to a higher dimensional space. I don't have to, but typically it goes to a higher dimensional space. So phi is sitting in a higher dimensional space than x. Why do you do this? It turns out that it's easier to separate training data using linear boundaries in the new space. And what you end up getting are nonlinear boundaries in the original space. So going back to this picture here, so in this picture here, I said that I could have separated the points with the blue points sitting on one side and the red points sitting on the other side if I used a nonlinear boundary like this, right? Something like this. Okay. So can I create that nonlinear boundary somehow through a linear boundary, but in a new space? So if I take all these points, and transform them into a different space, then there's a chance that I can get a linear boundary to separate those points in that new space, and that linear boundary, when I translate it back into the original space, is something that looks like this, that separates these guys. And actually, I'll show you pictures of that soon. Okay. So you can actually create nonlinear boundaries in the original space by doing this kernel transformation, right? Okay, why it's called a kernel, we'll get to in just a minute. But let's do a very, very simple example to illustrate why these nonlinear transformations could help with linear separation. So here are points. These are two classes, green and red. And they're basically quadratics. I mean, just a cooked up example. Quadratic. And there's no way to separate these things with a line. I could try drawing a line, and there's no way I could separate them using lines, right? So whatever line I draw, I cannot have all the greens being on one side of the line and red being on the other side of the line. But if I do a transformation, so this is the x1, x2 axis. If I took x1 squared, x2, and those of you who have taken 365 with me, maybe some of you have, you might have seen this example when we talked about it in the data science class. So if you transform it into the x squared x2 space, in the x squared, in the new space where x1 becomes x squared, x1 becomes x1 squared, sorry, x2 remains the same, then these curves, these quadratics become lines in this new space. And now I can see that I can separate these lines using a line. Okay. So, or another way to think about it is that this line, which separates these green and red points in this space, turns out to be a nice curve that separates the points in the original space. Right? So these nonlinear transformations can be useful. Okay, but actually implementing this nonlinear transformation is not that easy to do typically, and then doing all the computations in the new space might also turn out to be hard if you want to compute the optimum boundary using the SVM optimization in the new space. Well, it turns out this is where the kernel trick comes in, right? So if we look at dot products, so why are dot products important? Dot products are important because for linear classifiers, the boundary we saw can be written as a dot product compared to a threshold, W transpose X plus B bigger than 0. And we also saw in the SVM optimization written as a dual that the dual function, in order to compute the dual function, all we need are dot products, Xi transpose Xj. Okay, so, and in the new space, what happens to the dot product? In the new space, the dot product is being replaced by the dot product of phi of X and phi of R. Let's taking the dot product of two vectors in the original space X and R, that becomes phi of X transpose phi of R. I'll call this dot product the kernel, kappa. So here's the key point. If the classifier design and its implementation only require dot products, then we can use this kernel function to compute the dot product without explicitly computing phi. Without actually transforming the data explicitly, we can compute the dot products in the new space using this kernel. Okay, but is that true for the SVM? And it is true. We just talked about it. In implementing the SVM, W transpose X, you need to compare that with minus B, and that's a dot product. So this can be easily computed in the new space if we have the kernel, right? If you can also write this W in terms of the x's, and you'll get in terms of the x's like this, it's just a linear combination of the x's, then you get Xi transpose X. And there'll be only a few of them in the summation. Okay, so just a few dot products are enough to compute the boundary of the SVM for to determine whether the point is on one side of the boundary or the other. So implementation would be easy if I had this kernel function. Okay, all right. What about the design of the SVM? That's where, again, we saw that the dual, if you look at the dual version of the optimization problem, you just have dot products in the function here, which you can replace again in the new space. If you want to do linear boundaries in the new space, replace this with the kernel. Okay. All right. But now you need to ask the question, so what's special about the kernel, right? If I had my phi already, then I could easily have computed the kernel from phi, and then I didn't need the kernel. So what's special about the kernel? What's special about the kernel is that if I take a function of two vectors, X and R, right, and if it satisfies certain conditions, which are not that hard to check. Okay, the one is that it has to be continuous. We can form a function that's nice and continuous in the variables, the two variables. And if it's symmetric, so XR, K of XR is the same as, or kappa of XR is the same as kappa of RX. And if this function is positive semi-definite. So the notion of a function of two variables being positive semi-definite is a generalization of the idea of a matrix being positive semi-definite. In fact, this function is said to be positive definite if I form a matrix with various components, say kappa x1, x2, any arbitrary x1, x2, kappa x1, say so m, some m data points like that. Any m, x1 through xm. Not these are not necessarily your training data points. Any vector, m vector is my original space, and form a matrix like this with all the pairs basically. So kappa x2, x1. So this should be, sorry, this is x1, x1, x2, x2. Basically form a matrix with the ijth entry being kappa xi xj, and for any choice of this matrix, any m and any of the x's, or all choices of this, if this matrix is positive definite, then the function is said to be positive semi-definite. But there are tests actually to verify that this is easier tests than actually constructing every possible matrix and checking positive semi-definiteness. So if you can verify that the function, this kernel function, has these properties, then we can actually prove that there's a theorem that shows that there exists a phi. You may not know what it is, and actually the phi typically is written in terms of a series, okay? And it's some asymptotic limit of a series, but it doesn't matter. All you know is that there exists a function such that k or kappa can be written as the dot product of phi and phi r. And since you don't really need phi to compute the linear boundary in the new space, you just need kappa. As long as you can verify that kappa satisfies these properties, then you're done. You can use the kernel to compute your boundary. Okay, so let's look at some examples of and such a kernel is called a Mercer's kernel. Okay, and a commonly used example, of course, if you just make your kappa xr just x transpose r, there's no kernel, and that's a special case of a Mercer's kernel. That's trivial. But let's look at something more interesting. And this is called a radial basis function kernel, where kappa of xr is some monotonic function of the norm difference between x and r. Okay, and a commonly used version of this RBF is the Gaussian RBF, for which this monotonic function is of the form e to the minus beta times the norm squared for beta positive. And because it has this Gaussian bell shape, it's called a Gaussian kernel. Okay. Another example of a Mercer's kernel. So again, you can show that these properties are satisfied for these kernels. Okay. And a polynomial kernel is of this form: x transpose r to the power L, 1 plus n to the power L. And you can use different powers. So what's a big advantage of doing this? I can actually choose my kernel. Okay, as long as I can verify that it's a Mercer's kernel, I can use the kernel in place of the dot product, and that way, I'm automatically designing a separating hyperplane in my new space using those dot products and solving the dual optimization problem. Does that make some sense? That's why it seems like a magic card trick or something like that. So this is called the kernel trick for that reason. Okay, seems like a magical thing to do, but it actually allows you to design SVMs that produce highly nonlinear separating surfaces in the original plane with the same complexity as you would if you chose a linear surface in the or linear, just a hyperplane in my original space. Same complexity. Okay. So here are some examples. So if I used a linear kernel, this is for a 3-class SVM. So green, blue, and red classes. And so you probably can't see the colors all that well. You can maybe say that these kind of blue points, there's some red points sitting here and some green points sitting here and so on. So there's some margin violation between the classes. So this is like for, you know, again, for some choice of my margin violation parameter C. Okay, you get these boundaries. So linear boundaries are not going to do that great of a job of separating the classes, as you can see. There's a lot of violation. Okay, you can do actually a considerably better job using nonlinear boundaries, which these nonlinear boundaries that you see, these are very weird shapes, right? This was formed using a Gaussian RBF, right? So replacing the dot products in my optimization and in the implementation of my SVM, if I replace dot products with the kernel, okay, I get these boundaries in the original space, which are considerably better at separating the points of the different classes. Okay, and this is what I would get with a polynomial one. Again, how do you choose between these things, and how do you choose the parameter C and so on? You use machine learning methods called validation or cross validation. So you actually use a bunch of training data that you set aside, or label data that you set aside, and you compare the performance for different choices of boundaries and so on, different choices of kernels, and then choose the best one. But the whole point is that you might be able to do better than just linear boundaries using classifiers which have essentially the same complexity, which are highly nonlinear in the original space by using the kernel trick. And the kernel trick turns out to be much easier to do in the dual domain, because in the dual domain, the function has only these dot products. Okay. We are out of time. Did you get something out of this? And why the dual might be useful in this setting? Okay. Any of you took 365? No. Okay. I think there are some students who took 365, but they're not here today. So, all right. So, any thoughts on what you want me to do on Tuesday? It looks like there's not enough interest. Will the 8 of you at least show up next Tuesday if I were to give a class, or should I not bother? Boy, you guys are very quiet. Unmute, please. Let's have a conversation.
Oh, I will come definitely.
That's one. What about the rest of you?
I will come, and I will be interested if you talk more about the optimization in machine learning or reinforcement learning problems. Yeah.
I'll talk about stochastic gradient descent a little bit. Yeah, that would be related to. That's the most commonly used method. Yeah. And of course, we said a little bit about it when we talk about proximal methods, and they are useful when you have regularizers that are not differentiable. So that's used a lot in machine learning too. Okay. All right. So maybe I'll send an email to get a vote for how many people are going to actually attend on Tuesday before I decide whether we need to have a class or not, because it looks like people are busy with the final exams and things, and projects. All right, so hopefully I'll see you on Tuesday.